In this video, we're going to talk about the class of functions known as rational functions, and we'll try to understand as much as we can about their behavior. Shown on the screen here are four mathematical expressions, and although they're rather different from one another, there's something that they all have in common. Namely, each one of them is equal to one polynomial divided by another polynomial. And in mathematics, this is what is known as a rational expression. Once again, a rational expression is obtained by taking some polynomial and dividing it by some other polynomial. Now, we say that a rational function is simply any function, f of x, that can be expressed as p of x divided by q of x, where p and q are two polynomials of a real variable x. So, in other words, a rational function is just a function whose values are the values of a rational expression. Now, if someone were to just hand you a rational function and ask you to interpret it, you might be at a bit of a loss. So what we're going to try to do is be clear about some key things that we can understand about any rational function that someone throws our way. One of those things are the zeros of a rational function, right? As with almost any function that we may be given, we'd like to understand when it's equal to 0. We would also like to understand, as with polynomials, the asymptotic behavior of a rational function. And there are actually two key questions to be aware of. One of them has to do with so-called vertical asymptotes of the rational function. And the other question is to describe the so-called horizontal asymptotes of the rational function. Okay, so far those are just words on the screen. Shown here is the graph of what an actual rational function may look like. Okay, so the blue curve here represents the graph of an actual rational function. Let's see how the different features of the graph relate to the words that we just put on the screen. The zeros, of course, are the places where the graph of the function intersects the x-axis, right? They're the three dots shown in the picture. The vertical asymptotes of the rational function are the vertical dashed lines shown in the picture, and they basically represent values at which the rational function blows up and goes to either positive or negative infinity when that particular value is approached. The horizontal asymptote, on the other hand, is the green dashed horizontal line shown in the image. And it represents a value that the rational function approaches for very large values of x, if we go in either the positive or, in this case, in the negative direction. And finally, there's one other feature that we didn't have on our original list, and that's the so-called removable singularity of the rational function. And it corresponds in our picture to this sort of hole that we've drawn in the graph. A removable singularity is a point at which a rational function is not defined, but where it does not have a vertical asymptote. Now, how can we determine those characteristics using algebra alone? What if someone only tells us that our rational function is presented as the ratio of a polynomial p of x and q of x? Well, it turns out that the zeros of the rational function will basically correspond to zeros of the numerator, to zeros of p of x. And it turns out that the vertical asymptotes will basically correspond to zeros of the denominator, q of x. To understand the horizontal asymptote of a rational function, what we'll want to do is study the degrees of the polynomials in the numerator and denominator and how they relate to one another. And finally, to understand the removable singularities, or the holes in the graph of a rational function, we'll want to take a look at zeros that are common to both p of x and q of x. That's the basic idea. All right, so let's try to make all of this more concrete by considering a particular example. We're going to try to analyze the rational function r of x shown on the screen here. And that means we're going to try to understand its zeros and its asymptotic behavior, meaning its vertical and horizontal asymptotes, and also see if it has any removable singularities. Now, a good first step whenever you're working with rational functions is to factor as much as you can. So try to factor both the numerator and denominator of the function. That will make analysis easier. So notice first of all that we can factor a 3x out of the numerator. Then the remaining quadratic term in the numerator factors as x plus 1 times x minus 2. And finally, notice that the denominator factors as x plus 1 times x minus 5. All right, so here's our rational function in factored form. And one thing we notice pretty quickly is that there is a factor, namely x plus 1, that is common to both the numerator and denominator. On the one hand, that factor cancels out. But be careful, because the rational function is not defined at x equals negative 1, right? The value of x that makes that factor equal to 0. Rather, the rational function will have a removable singularity, or hole, at x equals negative 1. It's not defined there because it makes both the numerator and denominator of the rational function equal to 0, and 0 over 0 is simply undefined. So this common factor gives us a removable singularity at x equals negative 1. As long as x is not equal to negative 1, our function takes the form shown here. And since a ratio of two things can equal 0 only if the numerator is equal to 0, we see that the zeros of this function occur when x is 0 and when x is 2. On the other hand, this ratio will be undefined when the denominator is equal to 0, and that happens exactly when x is 5. That value will correspond to a vertical asymptote of our rational function, because at x equals 5, the function will, as it were, blow up to infinity. In summary, we saw that this rational function has a removable singularity at x equals negative 1, because that's a root of both the numerator and denominator. After it's canceled out, however, our rational function is identical to the function 3x times x minus 2 all over x minus 5. And that function is equal to 0 at 0 and 2, because that's exactly where the numerator is equal to 0. And it has a vertical asymptote at x equals 5, because that's precisely when the denominator is equal to 0. What about the horizontal asymptote of this function? Well, it turns out that there is no horizontal asymptote, and that's because the degree of the numerator of this rational function is greater than the degree of the denominator, which means that as x goes to positive infinity or to negative infinity, the numerator will rapidly outgrow the denominator and make it impossible for the rational function to approach any constant value. It must, in fact, go to either positive or negative infinity as x gets large, so there will be no horizontal asymptote. Let's try to focus more on horizontal asymptotes by considering a couple quick examples. This first example asks us to think about the horizontal asymptote of the function 2x over x to the fourth plus 1. All right, so the question here is what happens to the values of our function as x gets really big in either the positive or the negative directions. And the key thing to realize here is that the numerator is a linear polynomial, whereas the denominator is a polynomial of degree 4. Now, a polynomial of degree 4, as we know, grows much more rapidly than a linear polynomial. And so the denominator here will dominate as x gets large. In fact, the values of this function are forced to go to 0 for very large values of x, simply because the numerator can't keep up with the growth of the denominator. So the horizontal asymptote here would be the horizontal line y equals 0. And let's look at one more example. Here's a rational function where the degree of the numerator and the degree of the denominator are exactly the same. Let's try to think about what happens with the horizontal asymptote now. The key idea is that the numerator and denominator should grow at approximately the same rate. And to really understand what's going to happen in the long run when x is large, we're going to do the following. We're going to try to multiply this expression by x to the minus 2 over x to the minus 2. We're choosing minus 2 here because that matches the degree of the numerator and denominator, and by multiplying by this expression, we are not changing the value of our function, right? Since it's always equal to 1 as long as x is non-zero. after we multiply things out, we're left with the following expression. And the key thing to notice here is that as x gets very large, both the 1 over x term in the numerator and the 10 over x squared term in the denominator will get closer and closer to 0. And as x gets really large, their values will truly become insignificant. And so the value that f approaches will actually be 5 over 2. And that is nothing other than the ratio of the leading coefficients of the numerator and denominator of the original rational function. So the horizontal asymptote, abbreviated HA here, is the horizontal line y equals 5 over 2. In summary, the horizontal asymptotes of a rational function can always be determined in the following way. If the degree of the numerator is greater than the degree of the denominator, then there will be no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will always be y equals 0, since the growth of the denominator will dominate. Finally, if the degree of the numerator is exactly equal to the degree of the denominator, then the horizontal asymptote will always be the ratio of the leading coefficients of the numerator and denominator.